Look up at the sun right now. Not directly, never directly, but feel it. The warmth on your skin is real. The light reaching you has traveled 93 million miles through space to touch your face, and the space it traveled through was nearly 300 degrees below zero. This is one of the most fundamental paradoxes in all of science. The sun burns at millions of degrees. It is the most powerful energy source in the solar system, and the space surrounding it, the space that its light and energy fill completely, is almost unimaginably cold. Not a little cold, not winter cold, not the coldest place on Earth cold. We are talking about minus 270 degrees Celsius, nearly absolute zero, the theoretical minimum temperature the universe allows. How is this possible? How can the most powerful radiating object in our solar system be surrounded by near absolute zero emptiness? The answer changes everything you thought you knew about heat, about light, and about the nature of space itself. Before we go further, if this question has ever crossed your mind and you never got a real answer, hit that like button and subscribe. Every subscriber helps this channel keep exploring the deepest questions about the universe. Now let's answer this properly. Heat is not what most people think it is. We experience heat as warmth, something that flows from hot objects to cold ones, something that fills a room, something that travels. And in everyday life, this is accurate enough. But at the fundamental level, heat is something very specific. Heat is the movement of particles, atoms and molecules vibrating, colliding, transferring energy to each other through contact. This is the key. Heat transfer requires particles. It requires matter. When the atoms in a hot object vibrate rapidly, they collide with neighboring atoms and transfer their kinetic energy. The neighboring atoms speed up. The energy spreads. This is called conduction, and it requires physical contact between particles. There is a second way heat travels: convection. Hot fluid or gas rises, carrying its energy with it, while cooler fluid sinks. This is how your home heating system works, how the Earth's atmosphere circulates, how the oceans distribute warmth across the planet. But convection also requires matter. It requires particles to move and carry energy. Space has almost no particles. Space is not empty. It contains a thin scattering of atoms, the solar wind, magnetic fields, radiation. But the particle density is so low, far lower than the best vacuum humans have ever created in a laboratory, that conduction and convection are essentially impossible. Without particles to vibrate and collide, heat, as we experience it, cannot travel through space. But wait. If heat cannot travel through space, how does the sun warm the Earth at all? This is where the third mechanism of heat transfer comes in: radiation. And radiation is completely different from conduction and convection. Radiation does not require particles. It does not require matter at all. Radiation is electromagnetic energy, photons, traveling at the speed of light through the vacuum of space. The sun emits an enormous quantity of photons across the entire electromagnetic spectrum: visible light, infrared, ultraviolet, and beyond. These photons travel through the vacuum without needing anything to travel through. They carry energy across 93 million miles of near absolute zero space and arrive at Earth's surface, where they are absorbed by matter, the ground, the ocean, your skin, and converted into heat. The photons themselves are not heat. They are energy in transit. The space they travel through is not warmed by their passage. The photons cross the void without warming it, arrive at a surface with particles, and deposit their energy there, creating heat only when they interact with matter. This is why space is cold and Earth is warm simultaneously. The sun's radiation crosses the cold void unchanged. The void is not warmed because there is nothing there to be warmed. The radiation arrives at Earth and creates warmth because Earth has matter, particles, to absorb it. But here's what most people still don't understand. Why is space cold at all? If the sun is pouring enormous quantities of energy into space in all directions, why doesn't that energy warm the space it fills? The answer is that space has no temperature in the way we normally think about temperature. Temperature is a property of matter. It describes the average kinetic energy of particles in a substance. In a vacuum with no particles, the concept of temperature becomes almost meaningless. What scientists measure when they talk about the temperature of space, the famous -270 degrees Celsius, is something called the cosmic microwave background radiation. This is the thermal remnant of the Big Bang. The universe began in an extraordinarily hot, dense state, and as it expanded and cooled over 13.8 billion years, the radiation from that early hot state was stretched to longer and longer wavelengths by the expansion of space itself. Today, that radiation fills the universe uniformly in every direction, and its temperature, measured by the wavelength of the radiation, corresponds to about 2.7 degrees above absolute zero. This cosmic background radiation is the temperature of the universe itself. It is the baseline, and the sun's enormous energy output, spread across the vast emptiness of interstellar space, is not enough to significantly raise this baseline. The universe is simply too large. The energy gets diluted across too much emptiness. And here is where everything changes. Consider what happens to an astronaut in a spacesuit in Earth orbit. On the sunlit side, facing the sun, the suit can reach temperatures of over 120 degrees Celsius. On the shadowed side, turned away from the sun, the suit can drop to -150 degrees Celsius, not because space is that temperature, but because in the absence of an atmosphere to distribute heat, the only mechanism available is radiation, and radiation only warms surfaces that face the source. This is the real nature of temperature in space. It is not uniform. It is not a property of the void. It is determined entirely by what radiation a surface receives and how efficiently that surface radiates its own energy back into the void. The Moon demonstrates this perfectly. The lunar surface facing the sun reaches over 120 degrees Celsius, hot enough to boil water. The lunar surface on the night side drops to -170 degrees Celsius. The same airless world, the same location in the solar system, temperatures that differ by nearly 300 degrees, based entirely on whether a surface faces the sun or not. But that's still not the full picture. There is one more extraordinary thing about the coldness of space that connects back to the sun itself. The sun is not just hot at its surface. It has an outer atmosphere called the corona that reaches temperatures of 1 to 3 million degrees Celsius. This is far hotter than the sun's visible surface, which is only about 5,500 degrees. This is the solar corona heating problem, one of the greatest unsolved mysteries in astrophysics. The corona should be cooler than the surface below it, just as the air above a fire is cooler than the fire itself. Instead, it is hundreds of times hotter. Scientists believe this involves magnetic energy being converted to heat through processes that are still not fully understood. Magnetic reconnection events that release enormous bursts of energy into the corona. The solar wind, the stream of charged particles that flows outward from the corona at speeds of hundreds of kilometers per second, carries some of this energy outward through the solar system. And yet, despite this river of energetic particles flowing through the solar system, space remains cold. The solar wind's particle density is so low, roughly 10 particles per cubic centimeter near Earth, compared to the 10 billion particles per cubic centimeter of air at sea level, that even this energetic stream cannot warm the vacuum it moves through. Here is what stays with you. Space is cold not because the sun is failing. Space is cold because cold is the natural state of a vacuum. Heat requires matter. The universe is almost entirely empty. And the tiny fraction that is not empty, the stars, the planets, the thin streams of solar wind, is warmed by the exchange of radiation and energy between objects separated by vast cold distances. The warmth you feel on your face from the sun has crossed nearly 300 degrees below zero to reach you. It did not warm the space it crossed. It arrived at your skin, at the matter of your body, and deposited its energy there. You are a small, warm island in an unimaginably cold universe, warmed by a star 93 million miles away, across a void that its own light cannot heat. The sun burns. Space is cold. Both are true simultaneously. Not because of a paradox, but because heat and light are not the same thing, and space is not a medium that can hold heat at all. Look up at the sky tonight. The stars are burning. The space between them is nearly absolute zero. The light crossing that cold void is carrying energy that will warm nothing until it strikes something solid enough to absorb it. The universe is a cold, dark place, lit by fires that cannot warm the darkness between them.